Next, I'm going to briefly mention 19.4. You may remember that I didn't give any example problems for you to do from 19.4 because splines is something I'd like you to just skim this section. Our goal in spline interpolation is to come up with a smooth curve across a large number of points. Then if we want to extend across several points, then the interval-based interpolation that we learned in 19.3, like in the Lagrange interpolation, it won't work when we want to have our curve go smooth across many points. Instead, we'll seek a spline interpolation, which is piecewise polynomial interpolation. In modern applications, if you're going to be using spline interpolation, you are almost certainly going to be doing it in a computer which has packages available to help you with your spline interpolation. So I'm not going to cover spline interpolation because it becomes very specific and overly complicated given the fact that you're probably going to be using it in terms of application. So I'd like you to read it so that you can see the difference between spline interpolation and the type of interpolation we learned in 19.3, but I'm not going to give you any problems related to spline interpolation. Instead, I'd like to spend a bit of time looking at 19.5, where we're going to be using in numerical integration and differentiation. This you'll need to do a lot. In life, in your applications in the field that you're going to be working in, no one is ever going to tell you to use linear integration or linear differentiation. You're going to just come to some application where you you have production rates at many different times, and will ask you, what's our total production over this shift? And you'll need to integrate. And no one's ever going to tell you, now you need to integrate. They're just going to say, what was the total production from that shift? And you're going to use your measures of production rate from across that time in order to calculate it. And we're going to learn a couple different methods. Trapezoidal rule and Simpson's rule are what we're going to use most commonly. The trapezoidal rule is illustrated on the bottom left here in that figure, where we're basically just having a linear connection between the points where we have specific measures. And instead of integrating the curve, which we don't necessarily want to do. We just want to come up with a numerical approximation that integrates, assuming that each of our intervals is defined by this linear relationship. So instead of actually integrating the curve, we integrate under our lines, connecting those. That's the trapezoidal rule. So there we're clearly making an approximation, but it is often adequate. Usually, if you can use the Simpson's rule method, it's almost always better. Not always, but almost always, it's improved. The smooth curve in the bottom right example is actually strangely quirky, and Simpson's rule doesn't look like it's doing a better job, but in reality, it can accommodate most realistic curves much better. So we usually get an improved estimate out of an application involving Simpson's rule. Here we're using a parabola over each 3-point interval to try and estimate or try and approximate the integral. So we usually have less error in Simpson's rule than we have in trapezoidals, but because we're using 3 points in Simpson's rule, we usually have an unusual requirement that you have to have an odd total number of x values in order to make Simpson's rules work. I'll show you why in a moment. In the equations where we actually apply these, the rectangular rule is a case where we're just using uh, constant values instead of a linear interpolation. We just have a constant value for our interval, and it's given by that expressions where we're just taking the value of the midpoint of each interval and we're going forward with that. We almost never use that in reality. More commonly we use a trapezoidal rule where we have a bunch of x values, a, x1, x2, xn, all the way to b, typically and we're going to be using constant spacing between our points, where we're going to have our interval defined in the formula shown on the second line there as the interval size is given by h equals the quantity b minus a over n. So that tells us our interval size. And in the trapezoidal rule, we just apply a different weight to each observation. We give a weight of 1/2 to the first point and the last point, and a weight of 1 to all the other points. And then when we apply the formula, we get our approximation for the integral j, from the sum of h times the quantity shown. In Simpson's rule, what we need is a recognition that we're actually going to take an interval that involves 3 points. So h here is b minus a divided by 2m, where m is the interval size, and here we need to have different weights. Notice that our weights go in the following pattern. When I start at f0 and work towards f2m, you'll see my weights are 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. And it's the requirement that you have to have an odd number of points. That it is a characteristic of the Simpson's rule. And why we need that is because we have to end with the 4, 1 as our last two weights. You can't end with 2, 1. It just wouldn't work. So we need our weight pattern to be 1, 4, 2, 4, 2, 4, 2, 4, and you can have as many of these as you want as long as you end with 2, 4, 1. So that means we're going to have an odd number of points where we know the value of the function. Then we just sum up the values of the functions using that pattern of weights, multiply the sum by h over 3, and we have our estimate of the integral. Applications of numerical integration are actually very easy once you've done a couple of examples. Next, we're going to have some opportunities to estimate or approximate differentiation. Here we're going to be estimating the first derivative, and a few times we'll be looking at the second derivative of a function that's just too complicated, or where we're just not able to come up with an exact calculation of what the first derivative of the second derivative is. In these problems, we also have some x's and some f's where we have a known understanding of what the function is at those specific points. I'd encourage you to read your textbook. It's very clear on numerical differentiation, and the kinds of problems that we're going to illustrate you can find when we go through examples. We're going to largely come off the use of 3 and 5 point formulas for estimating the derivative of a function. Well, these are different examples where we're estimating the first derivative. We'll have some examples where we're looking at the second derivative as well. But in these, notice that what we're usually doing is the one that we'll use most commonly probably is 14.b, where that 14b is the equation number from your section of the text in 19.5. This really just uses the value of the function at the point just to the left of the point of interest, and the value of the function just to the right to the point of interest. We apply the weights of 1 and minus 1 to the function, and then multiply the sum by 1 over 2h, and we have our estimate of the derivative. This is nothing surprising. I'm sure you did these things when you learned about integration in calculus. And what's probably odd is that we'll sometimes want to use more accurate estimates, like in equation 15. You'll see that we actually have a very accurate estimate of the derivative of the function that uses 5 points to estimate the value of the derivative at point x equals x2. We would use the known value of the function 2 points to the left, 1 point to the left, 1 point to the right, and 2 points to the right. So f0, f1, f3, and f4 with the weights shown. So that's a very high order, much lower error estimate of the derivative there. It's a 5 point formula. But sometimes we'll need to do unusual things like I've shown in 14a and 14c. These are one-sided estimates. If you have a string of x's and f's that you know, you will be able to use a midpoint formula like 14 point B at all of the interior points. But at the left side of your series of points and at the right side, you need a different formula. To find the best estimate of the derivative at the left side, you'll want to use equation 14 point A. And to come up with the estimate of the derivative at the rightmost point, you can't use a centered formula like 14 point B. You'll need to use 14C, so that to estimate the, when you have 3 points, x0, x1, and x2, and the function f1, f0, f1, and f2, in order to come up with the estimate of the derivative at x2, you'll need 14c. So that's where you'll want to use the weights shown and sum up the values of the function in order to estimate the derivative. Again, if these seem a little daunting, once you've done a couple problems like this, I think you'll questions in this section should become some of the easiest that you will have on exam 2. I hope that's a good introduction. Please review the problems, and good luck with this week's quiz.